Today we will discuss backtracking. Suppose in this lockdown period you have decided to play Sudoku solving problem. In this problem, normally what we do, we try to fill the digits one by one, and some cases where we find that the current digit which is not helping us to lead to a solution, then we just ignore it or we discard it and try for the next digit. And we can call it that means the approach that we have followed, that means discarding the current one whenever we found it is not suitable. This approach is better than the net-based approach. Net-based approach where we have to generate all possible combinations of digits for this Sudoku problem and then try for every combination one by one. Right? That means we can say that we can reduce some number of trials as compared to net-based approach if we go for the first one, which we normally follow in case of our Sudoku solving problem. That means whenever we find that the current digit is not leading to the solution, we just discard it. That means we can say that our current proposal for the Sudoku problem, that means our current set of digits for the Sudoku problem, if it is not suitable, we have to remove it and try for the next digit. That implies that we are somehow going back. That means we are backtracking. For an example, suppose you have to make a series of decisions among various choices where you do not have enough information to know what to choose, and each decision leads to a new set of choices, and some sequence of choices may be a solution of your problem. In this context, backtracking is the way which will help us to find out the goal. That means we can say that backtracking is nothing but a methodical way of trying out various sequences of decisions until you find that one works. In support of these statements or the series of statements that we have covered, suppose this is the starting point. Asking questions indicates that what to do. You have two options, because I told you have to make a series of decisions among various choices where you don't have enough information to know what to choose. If I go back to Sudoku problem, assuming that in support of the statement that you have just quoted, that where we do not have enough information to know what to choose, that's why when the current setup digit, which is not supposed to be suitable, that means which is not leading to the solution, then what we do, we normally discard it and backtrack and choose the next digit, because we don't have enough information to know what to choose. Similarly here, from this point of view, I have two options. I may select any one of these two. Let us go for the left one. If I lead to this next point, then I have two options. If I go among left, that means I am following this path. Then unfortunately, as per the diagram is given, suppose I don't have any other options to go, and this is not supposed to be my goal. So that means it is called the dead end. So I have to come back. Immediate previous section. So from there I may move towards the another alternative, and unfortunately it is also supposed to be the dead end, so I have moved back. So as we don't have any other options to apply, I just come back here, because this path I have not yet applied. I move on this, then I come here, again I have two alternatives. Considering my approach moving towards left at first, which I have applied here also, then I move towards left, coming to this point, then I go or move further. Unfortunately it is the dead end, suppose I come back. Here also I had another alternative, I move on. Unfortunately it is also supposed to be the dead end as per the diagram is given. I come back here, then I follow this path, that means this one. Then there is a ray of off. Again I am here, I have two alternatives. I move on towards left first, it is a dead end, come back. Fortunately this is the success. So every time when I found at the dead end, I just come back and try for the other option. If it is a dead end, I come back, then I try for the another options. Okay, that means when we don't have enough information to know what to choose, each decision leads to a new set of choices. Okay, so if you consider this structure and just flipping it or rotating it towards right, it looks like a tree structure, where starting from root, if you move on to this path, then this is supposed to be your goal leaf node, and the other nodes that are the leaf nodes are not supposed to be your goal leaf node. These are the leaf node but not the goal leaf node. So this can be considered as the schematic diagram in support of the backtracking. It is a general example, or a general statement rather, or it is a diagram that we will consider in support of the backtracking. That means when there is a problem or the dead end comes out, you just come back and find the another trials, then come back and so on. So this is a general statement of the backtracking. So we can say that it is a methodical way of trying out various sequence of decisions until we find out one that works, until we find out the success. Okay, it can be thought of as searching a tree for particular goal leaf node, like this. Searching a tree, we move on towards right, no success. We move on towards these directions, no success. We move on towards left skewed, so there is a success. So that means it can be thought of as searching a tree for particular goal leaf nodes. Okay, so this is the preliminaries of backtracking. So we can say that it's a methodical way of trying out various sequences of decisions until we find that one works. So in general, sometimes we call that the algorithm which backtracks with intelligence are also called as backtracking. Okay, and basically in the search for fundamental principles of algorithm design, backtracking represents one of the most general techniques and many problems which deal with searching for a set of solutions, or which ask for an optimal solution satisfying some constraints, can be solved using the backtracking formulation. What I told, in the search for fundamental principles of algorithm design, backtracking represents one of the most general techniques. It is not as critical as other algorithm design techniques. It is the most general techniques. Many problems which deal with searching for a set of solutions, or which asks for an optimal solution satisfying some constraints. That means in your backtracking problem there should be some constraints that should be satisfied. Satisfying some constraints can be solved using the backtracking formulation. Fine. So we can say that in the search for fundamental principles of algorithm design, backtracking represents one of the most general techniques. Fine. Now we will go for mentioning some renowned person names who had the contributions in backtracking, and we can say that the name backtrack was first coined by D.H. Lemmer in 1950s around. Early workers who studied the process where one of the workers were R.J. Walker, who gave an algorithmic account of it probably in 1960s, and another two persons rather, is Ghulam and L. Beaumont, who presented a very general descriptions of it as well as a variety of applications. So Lemmer is a person, D.H. Lemmer. The name backtrack was first coined by him. So I have mentioned his name here. There are other four or three persons who had also the contributions in backtracking. So this is normally in 1960s and so forth. Fine. So in considering the backtracking scenario and whatever I told, then come to the section where we normally call, if I am supposed to solve a particular problem using backtracking, then how the solution is expressed. Unless and until I provide you a particular example, applying backtracking, that means I am solving a particular example using backtracking or a particular algorithm using backtracking, it would not be very clear for you to understand all the parameters which will be used to represent backtracking in general. In support of it, suppose you have already covered divide and conquer. In general, divide and conquer, suppose you have a problem P. If you divide it into sub-problems, and suppose the sub-problems are P1, P2 up to P of K, then as per the divide and conquer is concerned, you have to solve the sub-problems. You have to solve P1, you have to solve P2 and so forth. Then whenever you get the solutions of the sub-problems, finally you go for the combined strategy and you will assume that you are going to get the solution finally. So in general, it is expressed as subproblem P1, then subproblem P2, subproblem P3, subproblem P of K based upon certain divide criterion. Similarly, whenever you are mapping this concept, that means in general concept with a particular example, for an example mark shot, then you know how the problem is divided into subproblems. That means how an unsorted array calculating the mid index is divided, and you already know that division process continues up to a certain extent. That means based on certain criteria. That means whenever the split consists of one element in mark shot, then you need not to go further. That means you need not to go for further splitting. That means whenever the problem size is supposed to be very small, then you need not to go for the further splitting, because a segment consists of a single element is nothing but a sorted element for that segment. So this is the way that you can explain a particular algorithm, mark shot or even quick shot or even binary search, applying divide and conquer. But before proceeding to solve any particular example using divide and conquer, knowing some parameters that are normally used to express divide and conquer in general, it is not very easy task for the students to understand unless and until it mapped with a particular example. A similar thing may happen here. That means unless and until I go for a particular example applying backtracking, some of the parameters that are normally used for representing backtracking may be tough to understand. But let me try for a simple way to let you understand it. So in many applications of the backtrack method, the desired solution is expressible as an n tuple. That means whatever the solution that you are finally forming for a particular problem, it may be n queens problem, it may be sum of subsets problem, or it may be graph coloring problem. The solution of that problem is expressible as an n tuples, x1, x2, dot, dot, xn. You will get familiar with the terminology x1, x2. Whenever I will solve the n queens problem, you will better know that what will be the significance of x1, or even I will come later on. Definitely I will provide some simple example where xi, that means x1 or x2 or x3, that means xi in general, is chosen from some finite set si. You will got to know what is the significance of si later on. Often the problem to be solved calls for finding one vector that maximizes or even minimizes or even in general satisfies a criterion function p, x1, x2, dot, dot, xn. So there should be a criterion function, because I told you that in case of backtracking, you should satisfy certain given criteria, without which you cannot go for developing the solution. So in that case also there should be some criterion function. For an example, you can consider that if you are dealing with a graph coloring problem, you know that in graph coloring problem you have to color the vertices of the graph in such a way so that no two adjacent vertices have the same color. So you have to be very clear with the problem definition. For an example, you should follow the criteria of n-queens problem, where you know that n-queens problem is nothing but you have to place the queens, n number of queens in an n into n chessboard, so that no two queens attack each other. That means there should not be any quarrel between the queens. That means they should not share the same row in the chessboard, they should not share the same column in the chessboard, or even they should not share the same diagonal in the chessboard. So even if it happens, then definitely there will be a horrible situation. That means two queens attack each other. So avoid this kind of conflict. We have to be very careful about the criterion function. And sometimes it seeks all vectors that satisfies P. So let us go for an example that would make you very clear. Suppose m suffix I is the size of the set Si, the set that we are talking about, Si, finite set, from where xi should be chosen, and xi is a part of the tuple, where the tuple is of length xn, that is n. Okay, then there are m1, m2, mn, that means total n tuples, okay, that are possible candidates for satisfying the functions, that are the possible candidates for satisfying the function P. I told you about the criteria. There should be a criterion function P. Okay, we are here what we are mentioning. So there are m1, m2, mn, total n number of tuples that are possible candidates, okay, for satisfying the function P. What the brute force approach suggests? The brute force approach would be to form all these n tuples, evaluate each one with P, and save those which yield the optimum. That means in case of brute force approach, what I told at the time when I was talking about the Sudoku problem, then I told when a particular digit is not supposed to be fit, that means it is not leading to the solution, we just discard it and go for the next one. That means we backtrack. But in a naive based approach or brute force approach, what we do, we generate all the possible solutions and we go for checking it. That means the brute force approach would be to form all these n tuples, evaluate each one with P, that means the criteria, okay, and save those which yield the optimum. But what the backtracking suggests, the backtracking algorithm has as its virtue the ability to yield the same answer with far fewer than m trials. In case of brute force approach, all n tuples are tested, that means form all those n tuples, that means all m trials are given. But in case of backtracking, for solving the same problem, the same answer to receive with far fewer than m trials. So let us go for a simple example. Though I am telling that though I am mentioning here that I will come in my next lecture for n-queens problem, but for giving the example in support of those concepts, I have to use the n-queens problem here. But I assure you that I will come with my next lecture where I will cover n-queens problem using backtracking. So for example, I am again considering the n-queens problem. So n-queens problem, suppose in the chessboard, suppose this is the chessboard, suppose. So let me draw the chessboard here. Suppose this is the chessboard. Okay. Suppose it is a 4x4 chessboard. Okay. Fine. So 4x4 chessboard means n cross n chessboard, where you are dealing with 4 queens problem. N cross n chessboard, n queens problem, 4 cross 4 chessboard, so it will be a 4 queen problem. Suppose you have placed queen 1 here, so it blocks enter first row, okay, it blocks enter first column, and it blocks the diagonal. So I don't have the scope to consider the diagonal from upper right to lower left, because it's the first queen at the first row first column. So I am considering only the principal diagonal here. So queen 2 cannot be placed here, cannot be placed here, queen 2 can be placed only here. Okay. So that means when this was our first checking for queen 2, if it fails, we go for here. If it fails, we go for here. That means it's the place for queen 2 without any castle. Then you cannot place queen 3 here. You cannot place queen 3 here. You cannot place queen 3 here. You cannot place queen 3 here, because if you place queen 3 here, there is a conflict. If you place queen 3 here, there is a conflict. If you place queen 3 here, there is a conflict. If you place queen 3 here, there is a conflict. So if you go for approaching this solution, considering first column, first row for queen 1, second row, third column for queen 2, then if you go for checking it, then queen 3 do not have any suitable position to be placed. Queen 4 do not come to the picture unless and until queen 3 is being placed. So definitely you can reject the solution. You can reject the solution. That means you need not to check for all other solutions related to this. So that means you can reduce the trials. So once a partial generated solution is supposed to be not working, you need not to go for generating all other remaining solutions. So normally what brute force approach does? Brute force approach would be to form all these n tuples. So here backtracking can reduce the trials. So once this path is not helping you to process further, so where are you wasting time? You go back, you change its position. That means queen 2 needs to be shifted here. Then only queen 3 can be placed here. But in that case queen 4 do not have any ample scope to be placed in the chessboard. So entire concept is false. So you need not to go for queen 1 at row 1 column 1. So this process is wrong. So why are you wasting your time to check for the remaining combinations? So once you decide that this is the zone where you have come to the dead end, so we are moving further. Why you go for the further trials? So in this way you can reduce the trials. That's why it is written as the backtracking algorithm has as its virtue the ability to yield the same answer with far fewer than m trials. Okay. So what is the basic idea? The basic idea, you have to build up a vector. That is the solution vector. And in terms of this example again, here the column number for a particular queen under that row will be the part of the solution vector. So for an example, though I will come here in my next video about n queens problem. So let us take a solution here. 4 queens problem, 4 cross 4 chessboard. Suppose queen 1 is placed here. Suppose queen 2 is placed here. Suppose queen 3 is placed here, and queen 4 is placed here. You see that there is no conflict. Row 1, row 2, row 3, row 4. And what is the solution? So solution vector means this is like queen 1, that means row 1. So 1, 2, 3, 4. 1 means queen 1 and 1 also means row 1. Queen 1 is placed at column number 2 under row number 1. So it is 2. Queen 2 is placed at column number 4 under row number 2. So it is 4. Queen 3 is placed at column number 1 under row number 3. That is 1. Queen 4 is placed at column number 3 under row number 4. So it is 3. So it is a solution. It is one of the solution vectors for this problem. So here, to build up a vector which is called the solution vector, one component at a time, and to use modified criterion functions pi to test whether the vector being formed has any chance of success. That means I have written here the complete solution, but it achieves or it comes after some trials. That means here at first we consider queen 1 at column 1. So then you go for queen 2 at column 3 under row 2. Then queen 3 have not been has no option to be placed in a particular column because there is a conflict. So you need to change it. You make it 4 here. Then queen 3 can be placed at 2. Then queen 4 no option, so change it. Then you go for checking it with 2. That means partially generated vector may lead to the solution, may not lead to the solution. If there is a problem, that means partially generated vector is not going for a solution, then definitely you have to discard it. So similar concept is here. If it is realized that the partial vector can in no way lead to an optimal solution, then mi plus 1, that means the remaining mi plus 1 up to m of n possible test vectors can be ignored. Okay, so if it is just that I am going to the wrong direction, so why should I go for the remaining calculation? So for an example, if I place queen 1 here, I can place queen 2 here. In that case, queen 3 has not any suitable position to be placed, so I have to shift it. I have to shift queen 2 at column number 4. Then how it is generated? Queen 1 at column 1 under row 1, queen 2 at column 4 under row 2, then queen 3 can be placed at column number 2 under row 3, then queen 4 do not have any suitable position. So this position is wrong, this position is wrong. So because we don't have any other way to move from 4 to 5, because it is a 4x4 chessboard, we don't have other room to accommodate queen 2. So this is wrong. So initially you have to go back to the original solution, so change its position. So entire part is lost. So why should we go for checking or going for further trials for queen 4? No option. So we have to cancel it. Okay. Similarly, finally we can form it like this. So this is, if it is realized that the partial vector can in no way lead to an optimal solution, then mi plus 1 up to mn possible test vectors can be ignored. Okay, fine. Then there are a very interesting section that are the last part of the introductory section of the backtracking. So we can say that many of the problems we solve using backtracking, require that all the solutions that satisfy a complex set of constants. And for any problem, these constants can be divided into two categories. One category is called explicit constants and another category is called implicit constants. Okay, so what about implicit and explicit constants? Let us first go for their definition. I will come to the example, and I am sure that I will give you one example in support of this constant so that you can easily calculate which one will be the implicit and what will be the value of the implicit constants and what will be the value of the explicit constants and so forth. So what about explicit constants? Explicit constants is basically these explicit constants are the rules that restrict each xi to take on values only from a given set. That means explicit constants are rules that restrict each xi to take on values only from a given set. This xi, we are talking about the xi, that is what we mentioned here, that this xi, okay, chosen from a finite set. For an example, in support of that explicit constant, for an example, xi is greater than or equals to 0 if it is set explicitly. Then what will be the set? From this it is clear that the value of xi is greater or equals to 0, that means positive. So si, that is set, will be all positive real numbers. So the rules that restrict each xi to take on values only from a given set. Because in our discussion I told you that xi is chosen from a finite set si. So this is about xi, where xi is defined as greater or equals 0. So the set is all positive real numbers. So rules that restrict each xi to take on values only from a given set. I will definitely come with a problems where you can easily understand what is the explicit and implicit constants, and you can calculate it from there. So explicit constants depend on the particular instance, suppose it is I, of the problem being solved, and all tuples that satisfy the explicit constants define a possible solution space for I. I will come to the term solution space even when I will give the example there. And what about implicit constants? Implicit constants are rules. This is very simple to understand. Implicit constants are rules that determine which of the tuples in the solution space of I, which of the tuples, all possible solution space for I, define a possible solution space of I. Which of the tuples in the solution space I satisfies the criterion function, because I told you there should be a criterion function, and satisfying which you are leading to the solution. So it describes the way in which the xi must relate to each other. Okay, so already I have told the solution of the Queen's problem. I will again come back to Queen's problem in my next lecture. There you will find it, the implicit and explicit constants also. So let us take a problem which I have not planned to discuss in future. So these two constants, how they are related, what is explicit constants, what is implicit constants, from that example that would be more clear. Okay, so a very simple example I have taken in support of it. So let us again go for the definition of the implicit. Implicit constants are the rules that determine which of the tuples in the solution space of I satisfies the criterion function. So we'll verify it. Okay, let us take a very simple problem. This is sum of subset problem. Some of you may know sum of subset problems is a very simple problem. There will be a given positive integers, n number of positive integers are there, w1, w2 up to wn, or we can say that we have been given positive numbers wi in general. Here it is expressed as w1, w2, in general it is w of I, where the range of I is 1 up to n. That is same as w1, w2 up to wn. I is 1, w1, I is 2, w2, similar. Along with the positive integer m, so we have been given a positive numbers wi, that is w1, w2 up to wn, and m. And this problem calls for finding all subsets of the wi whose sums are m. That means this problem calls for finding all subsets of wi whose sums are m. That means if we have total 4 number of positive integers, that means n is 4. So we have w1, w2, w3 up to w4, and 11, 13, 24 and 7 respectively. Along with m, suppose m is 31. Okay. So one of the solution is, the problem statement says the problem calls for finding all subsets of wi whose sums are m. That means 31 is the output. So one of the probable combination is 11 plus 13 plus 7. 11 plus 13 is 22 plus 2, that is 24. 24 plus 7, 31. And another solution is 24 and 7. That is 24 plus 7 is 31. So using vectors, the two solutions are, number 1 we are taking, number 2 we are taking, that is integer 1 we are taking, integer 2 we are taking, and we are taking fourth integer. That means the solutions are expressed as the indices of wi, that is w1, w2, wn, w1, w2, w3, w4. So the solution is 1, 2 and 4 using the indices. That means 1, 2 and 4 is the solution, and 3 and 4 is another solution, that is third item and fourth item. This is a way to express the solution. So in general, all solutions are the k tuples. Here it is a 3 tuples, that is x1, x2 up to xk, where k is from 1 to n, maximum it would be n. And different solutions may have different size tuples. Here it is a 3 tuples, 3 size tuples, here it is 2, and so forth. So now you have to derive which one is the explicit constants and which one is the implicit constants. Okay. As per the definition, explicit constant says that rules that restrict each xi to take on values only from a given set, and implicit constraints are rules that determine which of the tuples in the solution space of I satisfies the criterion. Satisfies the criterion means M, the summation of the item should be such that, which should be M actually. The summation of the weight should be M, equal to M. The problem calls for finding all subsets of Wi whose sums are M. So now to find out implicit and explicit constants. First of one, explicit constants require xi. That means I told it is the rules that restrict each xi to take on values only from a given set. That means xi is nothing but the integer j. J is an integer and j varies from 1 to n. 1, 2, 3, 4. And here the solution is expressed in terms of the vectors which satisfies the problems. So what would be the implicit? Implicit constants are that no two be the same and the sum of the corresponding wi's to be m. That means here 1, 2 and 4 are the indices. These three items satisfies the criteria, whereas 1, 2, 3 and 4, these four are the item indices. So explicit constants require xi belongs to j, where j is an integer and j lies from 1 to n. Here n is 4. So the probable value of j will be 1, j will be 2, j will be 3 and j will be 4. But implicit constants require that no two be the same and the sum of corresponding wi's be m. So here this is satisfying the criteria. That means 1, 2 and 4. It is not like 1, 2, 3, 4 all. No, 1, 2 and 4 satisfies the criteria. 3 and 4 satisfies the criteria. So since we used to avoid generating multiple instances of the same subset, that means 1, 2, 4 is equivalent to 1, 4 and 2. Whatever the combination is, ultimately it reads to 31. Anybody can say 1, 2 and 4, anybody can say 1, 4 and 2. 1, 4 and 2 and 1, 2 and 4 are same. So we can avoid those subset having repetitions. That means multiple instances of the same subset. Another implicit constants that is imposed here is that x of I lesser x of I plus 1. It is another issue. So here I think the concept of explicit and implicit constants are clear. So xi, where it is j is an integer and j is lying from 1 up to n. You have total 4 items, 1 to 4. So j is from 1 to 4. And implicit constants that no two be the same, and the sum of corresponding wi's be m. You have taken only 3 here, 1, 2 and 4. That means index of w, which is 1, which is 2, that means first item, second item and fourth item, that are satisfying the criteria. Similarly, this can be formulated in other way. Suppose a simple formulation of the problem is where the solution subset is represented by an n tuple such that xi equals to 0 if wi is not chosen and xi equals to 1 if it is chosen. So here we are mentioning the indices using which we are showing the solution. But in the second approach, it will be expressed in terms of 0 and 1. That means if the item is chosen, it is 1. If the item is not chosen, it is 0. So similarly, so what will be the explicit constants? So the explicit constants is xi, which is either 0 or 1. That means if chosen, if not chosen. And the solution is, you have taken the first item, second item, third item not, and fourth item. That means first item taken, that is 1. Second item taken, that is 2, that is again 1. Third item is not taken, so it is 0. Fourth item taken, so it is 1. And in this combination, you have not taken first and second item, so the field will be 0, 0, 1, 1. 0 for not considering first item, second 0 for not considering second item, 1 and 1 for you are considering third and fourth item. So the solution is 1, 1, 0, 1. First item taken, second item taken, third item ignored, fourth item taken. First two item ignored, third and fourth item taken. So explicit constants gives you what will be the combination, that means either 0 or 1. And implicit constants will give you for all xj equals to 1, that means those who are 1, for which summation of wj equals to m. That means if you take this combination, here the summation is 31 because first item, second item and fourth item taken. So this is another way to represent the solution of the same problem, where the explicit constants are 0, 1, 0 and 1, and the solution is this one, and the implicit constants for all xj equals to 1, where summation of wj equals to m. So the solution of these instances, above instances are 1101 and 0011. So this formulation expresses all solution using a fixed size tuples. Thus we conclude that the tuples that satisfy some constants. And thus we conclude that there may be several ways to formulate a problem so that all solutions are tuples that satisfy some constants. So in this case, all the tuples are in these formulations actually. Here all the solutions using a fixed size tuples. This is 4, this is 4. But here it is a variable size tuples. Here it is 3, it is 2. Okay. So here it is fixed size because the field which is not using, we put it 0 here. But here the field which is not using, we are not mentioning here. So two approaches of the same problem. So we can say that implicit constants here, explicit constants are nothing but the indexes actually. That is an integer. J is an integer and j lies from 1 to n. And here it is 0, here it is 0 or 1. Okay. And here it is implicit are for which you are getting the solution 1, 2 and 4. Here for which you are getting the solution, that means for all xj equals to 1. So and the w of j equals to m. Okay. And the solution space is of 2 to the power n distinct tuples. The same problem, sum of subset problem, can be expressed in two approaches. So I think now the concept of implicit and explicit constraints are very clear. Explicit will give you basically the rules that restrict each xi to take on values only from a given set, whereas implicit this is explicit, and the implicit constants are rules that determine which of the tuples in the solution space of I satisfies the criterion function. So criterion function means the sum should be m here. Okay. So first of all, fix up the explicit constant, then go for the solution, then you can easily find out the implicit constants. Okay. Similarly, here the explicit constants you have decided, then go for the solution. So easily you can go for the implicit constants. So here also you formulate first of all explicit constants, what will be the explicit constant, then you get the solution, then you finally identify which will be the implicit constants and so on. Okay. So we have discussed the main general part of backtracking. So starting from the beginning, we have covered how the problems can be solved using backtracking and how the solutions can be expressed. We have expressed in terms of the tuples and so forth. So the same types of strategy we'll find when we'll deal with the particular problems. For an example, that is n-queens problem as per your syllabus, or even a graph coloring problem, then definitely we'll find out how the solution is expressed in terms of this tuple, and how the selection criteria, how the criterion function, how the criterion functions are there to be checked so that it cannot be violated. And once a solution is going to be constructed, and if it is found that the partially generated vector is not sufficient to go for the leading part of the solution, then we have to ignore it and so forth. So we have to think of the basic idea, we should follow it at the time of solving any particular problem. So here we have given one example of the sum of subset problems in support of implicit and explicit constants. My advice is all of you to go through Sahani because backtracking algorithms are well expressed in Sahani's book. You may consult any other standard books, but I think Sahani is a very good book for backtracking. So in my next lecture I will come to another very important section of backtracking, which is basically state space search tree generation. Because if you know the constraints formulation, that means implicit and explicit constraints formulation, and if you know how to form the state space search tree, then it would become very easier to build up the state space search tree for n-queens problem as well as graph coloring problem. Okay, so wait for the next lecture to arrive. Thank you.